Most people would learn to code by standing on the shoulders of giants and using game engines and high-level languages. I'm not against that, and in fact, that's how it should be. But sometimes you might just want to go to the base of everything and to understand how everything works under the hood. Basically, no engines, no libraries, just you and the CPU. Hi, I'm Kenway, and this is as close as it gets to the metal. In this series, we're building a platformer game from scratch in assembly. And in this part one, we'll try to understand the basics of how assembly works and how many types of architectures are there, why we have different syntax for assembly, what are registers, and how we interact with them in order to perform our operations. To talk to the hardware, we need a translator and a playground. You will need NASM, the NetByte assembler, which we will use for this video. It translates our code to machine code. There are other kinds of assemblers as well, but for the purpose of this video, we will use only NASM, but we will understand the other ones as well. DOSBox, on the other hand, is our emulator that we're going to be using to simulate a 16-bit environment. Now, DOSBox is a 32-bit environment, but all the games that are based on DOS are 16-bit, and it gives us direct access to video memory without the modern operating system blocking us, because if you use Windows, it would put some blockage in our way, so we can't really use it to directly access the video memory. A text editor like VS Code or NeoVim or Atom, and some passion to question why, to basically everything. That's how it works. That's how it works in learning. In assembly, we don't write ones and zeros anymore. Rather, we use mnemonics and short abbreviations like move to move data, add for addition, push to drop data onto the stack, and then pop. If you're using something called the subroutines, then you would have to pop the variables back as well, which we will talk in a later video, and we will need to use subroutines. The assembler takes our mnemonics and bakes them into the binary opcodes that the silicon basically understands. Coding here means manual labor. You're directly manipulating registers that are these tiny lightning fast storage spots inside the CPU. You're not asking the OS to create a variable. You're telling the CPU that, hey, this is the bucket where you want to put the number inside. Assembly isn't just one size fits all. It depends on the hardware architecture. We have different kinds of hardware architectures. You would have heard the name x86 and x86-64. This is the king of desktop. x86, the classic one, is a 32-bit style, while the x86-64 is a modern 64-bit powerhouse. We will discuss what the 64 and 32-bit means in this situation. ARM, on the other hand, is the engine that is used in iPhone and Macs. It's built for efficiency. We have RISC-V, which is the new open source Rebel, basically no royalties, and it's totally modular, and it's gaining a lot of popularity among the nerds today. MIPS is if you have played Nintendo 64 or PlayStation 1 games, then you have played games that were built on MIPS. It's the gold standard for learning how reduced instruction set works. So what's the actual difference between a 32-bit architecture and a 64-bit? A 32-bit CPU eats the data in 32-bit bytes. A 64-bit CPU doubles that, which means more data per cycle and faster maths. A 32-bit CPU is mathematically capped at addressing 4 gigabytes of RAM, and 64-bit can theoretically hit 16 exabytes of RAM, but we don't really have that much RAM. That's why modern games need 64-bit and not 32-bit, because they need more processing power. In 64-bit, our registers grow. Basically, in 32-bit, we have what we call the EAX register, which is a 32-bit register, while in 64-bit, that EAX register becomes a 64-bit register now called RAX. We also get 8 new registers, That means that our CPU has to talk to the slow RAM much less often. Even on the same CPU, the flavor of your code depends on your assembler. So as we discussed, we'll be using NASM, which is our choice for the series. It's open source, it works everywhere, and uses clean Intel syntax. We also have MASM, which is the Microsoft's assembler. It's great for Windows, but it's very macro heavy, and it has these labels and commands that you have to memorize, which you can, which is a good thing, but we won't be using this for the sake of this video. FASM is another assembler, which is basically the speed demon. It's so efficient that it can compile itself. For this series, we're sticking with NASM, and it's the perfect balance of power and simplicity. So today we aren't just talking theory. We're going to use the x86 assembly, the NASM assembler, and the DOSBox environment, because it's the easiest way to access the video memory to draw our first pixel. ORG100H. So what does that mean? This is the origin of your code. This tells the assembler that the program will be loaded at the offset of 256 bits in its memory segment. This is a requirement for the .com file that will be generated when we compile our program. In the DOS era, the first 256 bytes are reserved for the program segment prefix, which contains the metadata about our program. So it's just setting that offset. Move AX, 13H. This moves the value 13H into a 16-bit AX register. In BIOS terms, 13H is the ID for VGA mode 13H. This mode is famous because it provides us with a resolution of 320 x 200 pixels with the 256 different colors. Now, if you look at the maths here, and 320 x 200, that means 64,000. That means 64,000 pixels. This fits perfectly into our single 64 kilobytes of memory, because if we remember, we're using 16-bit environment. That means that 2 raised to power 16, that's 65,536. So we can perfectly fit everything in our memory space, and it makes it the easiest mode for assembly game developers to manage, if that's even a field. Int 10H is the video interrupt. It pauses your program and hands the control to BIOS. The BIOS looks at the AX register, sees the 13H, and tells the graphic card to switch from text mode to the graphics mode. It's really doing nothing other than that. The move AH, 0CH is very interesting because we don't know, we haven't seen that register, right? That's because the AX register is a 16-bit register. And what AH and AL is that the AH is the high byte of the AX register, and AL is the low byte of the 16-bit register. So setting AH to 0CH tells the BIOS that I want to use the write function, the write graphics pixel function. Now we're using AL, which holds the color index, and it's the lower byte of our AX register. In the default VGA palette, 0FH means the bright white color. If you change it to 04H, the pixel color would be red. So what we're doing here is basically using color index to paint our first pixel, telling what color our first pixel should be. And in our case, it should be bright white. The move BH, 00H is the video page. Now, this command, we don't really need it in our code. It basically tells to move to page 0, and VGA mode, there's only one page, which is page 0, so we don't really need to set this, but it's a good thing to set it, because when you're using different kind of environment, you might need it over there. Now, move CX, 160 and move DX, 100 are interesting because CX is the horizontal coordinate and DX is the vertical coordinate. So CX being the horizontal coordinate, we know that our total pixel on the resolution scale is 320 pixels, right? That means if we divide that by 2 and then we get 160. So we want to draw our pixel in the middle of the screen, so we're using 160 and 100 that draws the pixel at the very center. Int 10H is the video interrupt. It's another video interrupt. The BIOS reads all the registers we just set, the AH for the function, the AL for the color index, the CX for the x-axis, the DX for the y-axis, and physically changes the color of that specific coordinate on your monitor to bright white in our case. Now, this is some of the cleanup code. Move AH, 00H, and then using int 16H. This is a keyboard interrupt. The function 00H tells the BIOS to halt the CPU until the key is pressed, because without this, our program would finish so fast that we would never be able to see our pixel. Now, move AX, 03H is another thing that we need to do before we end our program. It's basically, it comes under the cleanup of our code in the end, and it takes us back to the text mode. So from graphics mode to back to text mode. Move AX, 4C00H, or you can even call it 4CH, is the terminate process function for DOS. And it basically terminates our program, and our program ends without any kind of errors, and we get returned to the DOS screen. In the next video, we'll discuss more about how to bring this pixel to life and to animate it. We have successfully bypassed the abstractions and forced the hardware to draw for us. It might just be one pixel today, but it's the foundation of every game ever made. If you want to keep on watching, or if you want to support me as a creator, then you can by subscribing to our channel. It's free. The button should be just down there. And thank you so much. Stay tuned.